let's talk about minerals. That's what a lot of geology, what people first think of is minerals, because really that's the building block of all the rocks that we're going to be talking about as the semester goes on. This image that you're looking at here is not fake. Those are people on the left-hand side in a cave in Mexico that is at about 120 or 140 degrees. The air is not breathable in there, but there are these giant gypsum crystals that have grown inside this cave that is full of superheated gases and fluids. So it's pretty remarkable. These minerals, normally, they're tiny, but sometimes in the right conditions, they can grow to be these enormous crystals when they form under the right conditions. But minerals, they have a specific definition. They're not just, you can't call anything a mineral. So what is a mineral? Over on the left-hand side here is a picture of some shale that has some pyrite crystals growing in it. Pyrite's a mineral, and it's a mineral because it fulfills 5 specific things. It's naturally occurring. So that means minerals that are only formed by growing them in a lab wouldn't be considered mineral. They're inorganic, so they have the constituents that make up the mineral themselves are not organic molecules like methane or anything with a complex hydrocarbon structure. Minerals are crystalline, meaning that they have a crystal structure to them. And they're solid, but they're solid at the conditions of Earth's surface, which is 1 atmosphere of pressure, means what we feel at the surface of the Earth with 1 Earth atmosphere above us, and at about 25 degrees C. That means that certain things that might be minerals elsewhere, depending on how your definition changes, are not minerals on Earth. So liquid water is liquid at average Earth surface conditions, but once you get it down to 0 degrees C, it would fulfill all of these criteria. But because it's not solid at Earth surface conditions, ice does not count as a mineral. And then it has to have a specific composition. What we mean by that is every time you find a piece of pyrite, it's pretty much going to have the exact same composition. It's going to be iron and sulfur. And all minerals are like that. They might have some small variations that occur, but in general, they have a specific composition that's the same every time. If you don't fulfill these requirements, you're not a mineral. You might be something like coal or obsidian or materials that are mineral-like, but they're not true minerals because they don't fulfill these 5 requirements. Now, if we're going to put a mineral together, we need to bond all the atoms that make up a mineral together in some way. And hopefully this might be a review to some of your chemistry classes you've taken in the past. But if we're going to build minerals, we're going to do it by taking atoms and bonding them really one of 3 ways. One of them is by having an ionic bond, which is an exchange of an electron. So you actually transfer an electron from one atom to the other. So our example here is a sodium atom transferring an electron to a chlorine atom. And that's because sodium has 1 too many electrons to be in a stable, what we call a noble configuration, like the noble gases, things like helium and argon and krypton and things like that. And chlorine is missing 1 electron in its outermost shell to be in that configuration. So energetically, the most efficient thing for it to do when these 2 atoms get close together is that the sodium gives up an electron and the chlorine takes it. Now, this kind of bond is not a particularly strong bond because there's only really 1 electron involved. So minerals that bond together like this tend to be soft, and they tend to be soluble. They'll dissolve easily in water. That bond can be broken apart. So sodium and chlorine, you put those together, you get halite. Halite is salt. So salt is an example of an ionic bond that's easy to dissolve in water because it is just a single electron exchange. Now, if you want things to get a little more, be stronger bonds, you might use something like a covalent bond. So covalent bond, you're sharing electrons to complete the shells. So although this example here isn't a mineral, it is a covalent bond. We have hydrogen and oxygen bonding covalently. They are sharing electrons In the mineral world, minerals that are covalently bonded, something like diamond, will be hard and they'll be insoluble, so they don't dissolve in water very easily. Most minerals have a lot of covalent bonds in them. So most minerals tend to be pretty hard and they don't tend to dissolve easily in water. And then finally, some minerals you're going to find have a metallic bond. They tend to be things that are metals. Gold has metallic bonding. And that means that all of the nuclei of the atom, all of the protons and neutrons sitting in the core of the atom are just packed close together. And all of the electrons that are part of the different atoms just act as a sea of electrons around all of these nuclei. So they're really good for atoms that have a lot of electrons and require a lot of electrons to move around to have this move into a noble configuration. So minerals that have a metallic bond are dense because all of those nuclei are packed closely together. They're conductive because they're also packed closely together again, and they have all these electrons that they're sharing. And they can be malleable. The bond doesn't need to be in a specific configuration. So like think about gold. Gold you can hammer out so thin that you make gold leaf because the bonds are so malleable in that metallically bonded material. So most minerals are made of one of these three bonds, or actually combinations of bonds. So they might have some of the atoms are bonded covalently and some of them are bonded ionically. They can be a mix as well. But what you really need to think about is that for a mineral to be a mineral, this bond has to produce something that has a regular structure. And that's what we call a crystal lattice. So they bond together to form a structure. Sodium and chlorine and salt bond to form this cubic structure that is the crystal lattice of that mineral. And these lattices are unique to the minerals. So certain minerals might share the same form, but the lattice itself is a sodium and chlorine lattice in a cubic form like this is unique to halite, unique to salt. And these crystal lattices also help lead to the mineral properties. So when you break a piece of salt, you get these little cubes because the crystal lattice is formed in these in a cubic shape. So the shape that crystal lattice, where those bonds of the mineral come from, and the crystal lattice that forms, dictate the properties of the mineral. So a mineral like salt that is cubic when you break it apart, it's soft and is soluble. All of that is thanks to the ionic bonds that it has and the crystal lattice that forms when those ionic bonds come together. Now, minerals can form in a lot of different conditions. Minerals can form directly out of liquid water. We'll talk about that in a second. So they can crystallize out of water that's full of atoms. They might form from another type of liquid like magma. Magma is molten rock. It is liquid rock. And when it crystallizes to form things like in this picture of granite, that granite is forming out of or the crystals. In here, you're seeing pink plagioclase feldspar, white plagioclase feldspar, or pink orthoclase feldspar, white plagioclase feldspar, black hornblende, gray quartz. All of these different minerals are crystallizing out from the liquid magma as it's cooling. Sometimes you can actually get minerals to form directly out of a gas. So in the bottom right-hand corner is a picture of John Ewart from the U.S. Geological Survey sampling sulfur coming out of a vent. And all the yellow is sulfur that's crystallizing directly out of a gas into the air when it cools. So you can actually get minerals to form directly out of a gas. And then kind of the weirdest one for most people to think of in the top right is minerals forming directly from a solid. So these big red minerals in here are garnet crystals. Now, garnet will form when you take a rock and you put it in a new and pressure temperature condition, and it has to find a new happy place, for lack of a better term, a new equilibrium. And that garnet will form with the rock remaining solid. The atoms will rearrange and you'll get garnet to crystallize directly out of that solid. So we can think about this in some other ways, right? What are some of the ways that minerals are forming? Well, one of them is that if you just take a liquid and oversaturate it with atoms. The example here is think of a lake out in the desert. As it dries up, that atoms in that water will get more and more concentrated until they're so close together and they bump into each other so much they start to bond. That's saturation. And supersaturation happens when you just have evaporated off so much material, so much water, let's say, that you are just having bonds form so readily that you're crystallizing out lots and lots of salts. So in this case, oversaturation is when you just take a liquid and fill it so full of atoms of specific elements that they just start bonding spontaneously. Another thing that happens is that if you have a drop in temperature, you can get minerals to start forming. So a drop in temperature might be something we picture in magma. As the magma cools, the kinetic energy drops, so the atoms aren't moving around as much and they begin to bond. You can think of the same thing as in water. So the arrow that you see there that's marked by a minus delta T, that just means the temperature is dropping. If you take water and cool it at the same pressure, it will form ice because those water molecules will begin to bond together because the kinetic energy of the whole system begins to drop. The atoms aren't moving around as much. If atoms are moving around a lot, they don't like to bond together. If molecules are moving around a lot, they don't like to bond together. Slow them down by cooling the temperature, dropping the temperature, and they begin to bond and form minerals. Lastly, you have this minerals forming by re-equilibration. It's more or less a chemical reaction that's happening. So again, here's a lovely rock full of garnet. New minerals are forming because old minerals were put into some new pressure and temperature condition. So the rock that originally was formed was exposed, let's say, to a big mountain building event where it feels high pressures and high temperatures. And the atoms in that are no longer happy in the minerals that were originally there. So they start to move around and form new minerals that are stable in those high pressure and high temperature conditions. We call that a re-equilibration. And you form things like these garnet crystals that originally were in a rock that was full of minerals like olivine and pyroxene and plagioclase. So we'll talk about the different types of minerals soon. But the different minerals that were there were no longer stable, so the atoms rearranged and formed something new. So that's kind of our introduction to minerals. We'll talk a little bit about what the different types of minerals are in the next video. So look forward to that.